Okay, we have got now a paper called Amylase and Bread Farming, which will tell us an integrated view on these two phenomena for the 8th week. So this is a paper published in 2008, by the way. So for several thousands of years, man has used wheat and other cereals to produce bread, and with an average consumption about of 65 kilogram of bread per capita per year in Europe, it remains an important constituent in balanced healthy diet. So the convenience, taste and freshness just determine to a great extent the appeal of bread products and are expected to remain the driving factors for purchase of the bakery products. So, however, the shelf life of fresh bread is just rather short, and during storage, a number of complex physical-chemical changes occur, which are collectively referred to as staling, and the bread gradually loses its pleasant aroma and the crispiness of its crust. And in addition, the rigidity of breadcrumb increases, crumb resistance deteriorates, and the water evaporates from the surface of the sliced bread, resulting in a perceived firmer and drier feeling crumb. And several additives aim to improve the physical-chemical shelf life of bread with specific amylase, in particular Bacillus stereothermophiles maltogenic alpha amylase, being very effective anti-staling agents. So the molecular changes that happen in bread during storage and which are responsible for the firming and staling phenomenon are quite complex and involve multi-constituents and mechanisms. And it's generally accepted that the retrogradation and recrystallization of starch, specifically of the short amylopectin side chains, plays a major role in the bread forming after the initial cooling happens. So we have to be careful that these reassociations in the starch fraction alone are insufficient to explain the crumb forming and loss of resilience, and indeed the extent of the starch molecule ordering, such as the crystallization during storage, does not necessarily correlate well with the crumb forming, particularly in amylase supplemented breads. So in addition, although next to starch crystallization, water migration is also widely accepted to be a very important aspect of firming. So the change in water distribution between the biopolymers in the crumb are often neglected in bread firming, and in short, despite much research, the crumb firming and consequently the anti-firming properties of amylase are still insufficiently understood at the molecular level. So the researchers present a coherent view on crumb firming and how it is impacted by the amylases. They use their own experimental data and also they benefit from the literature. And the latter one, such as the network formation, allow the relating macroscopic bread properties such as crumb forming and loss of crumb resilience with molecular related events. They introduced the major players involved in bread firming, in particular the different flour constituents including starch, gluten, and albanoxylane and amylases. So then they present how they are involved in the different steps of bread making, such as the dough and oven stage, and they present a view on crumb firming during the storage and the anti-firming properties of amylase. If we're gonna think about the wheat flour constituents, it is the major ingredient in the bread making, and it mainly consists of the starch, water, proteins, and non-starch polysaccharides. Starch is comprising about 70 to 75% by weight. Water comprises 14%, and proteins comprise 10 to 12%, and non-starch polysaccharides comprise the 2 to 3%, and in particular arabinoxylanes and the lipids comprise the 2%. So during the different steps in the bread making process, complex chemical, biochemical, and physical transformations take place, which affect and are affected by the various flour constituents. So then the starch is the most important storage polysaccharide of cereals, and it occurs at intracellular partially crystalline granules with a high degree of order as demonstrated by their biorefrigerants when viewed under polarized light. In contrast to most plant starch, wheat starch granules have a bimodal size distribution consisting of large lenticular and small spherical granules. So the milling mechanically damages some of the starch granules in wheat flour, and damaged starch is more susceptible to amylolytic attack and has an increased water holding capacity at room temperature than the native undamaged starch granules. So the starch granules are characterized by the different levels of structural organization, including the amorphous and partially crystalline growth rings and lamella and partially crystalline blockles. At a molecular level, two glucose polymers are the major constituents, for example, the essential linear amylose and the high branch amylopectin. Amylose corresponds to 25 to 28%, and highly branched amylopectin corresponds to 72 to 75%. Amylose consists of linear chains of 500 to 6,000 alpha-1,4 linked D-glycopronosyl units, with a fraction of the amylose molecules being slightly branched by alpha-1,6 linkage. And in contrast, yeast amylopectin is built up by the linear chains of predominantly 6 to 24 hours, 24 um, linked D-glycopyranosyl units, not ours, with a small fraction of linear chains with 25 to 36 units. Again, we can see the repeating glucose units over there. So irrespective of their rank, all these chains are connected by alpha-1,6 linkages, since we are talking about amylopectin. So this way, a very large and highly branched polysaccharide of up to 3 million glucose units is formed, and the cluster structure model of amylopectin with polymodal chain length distribution and the random nature of branching is nowadays generally accepted. So in the cluster model, the short chains, the unbranched outer A chains and the shortest inner branch chains form helices which laterally associate as crystallized and make up a single cluster, while the longer branch chain extend into 2 to 4 clusters respectively. And while amylose and the amylopectin backbone and branch points make up the amorphous parts of the starch granule, different packaging of the amylopectin side chain has given rise to different crystal types, and native cereal starch have an A-type X-ray diffraction pattern, while the retrograded starch shows B-type crystallinity, and the former crystalline structure is relatively compact with the low water content, while the latter one has a more open structure with a hydrated helical core. So we can see that the starch undergoes unique transformations during the heating and cooling in the presence of water, and upon heating, starch suspensions above a characteristic temperature, such as the gelatinization temperature, which corresponds to the glass transition temperature in excess water. Structural order of the starch granules is irreversibly destroyed and biorefrigerants is lost, and this process is termed gelatinization. Events associated with the loss of biorefrigerants include the melting of amylopectin crystalline lesions, which transform the partially the crystalline granules into an amorphous state, and here you can see granule swelling occurs and partial disruption happens due to the increased water uptake and the limited starch solubilization. This is referred to as amylose leaching, and an increase in viscosity takes place. So the leached amylose can then form inclusion complexes with polar lipids, and these are endogenously present in the wheat starch, and we can say that these kind of, let's say, particles may be added during bread making, and under the limited moisture conditions, the starch crystal melting temperature ranges increase to higher temperatures, and a second endotherm is resolved by differential scanning calorimetry. And during cooling of the gelatinized and post-starch suspension, the amorphous linear amylose polymers associate into the ordered structure, or even under favorable conditions into a B-type crystalline state. Over time, amylopectin also decrystallizes, and initially a continuous amylose chains, which in their turn quickly further develop into a very stable crystalline structures, and amylopectin recrystallization is a much slower process occurring within and between the swollen and deformed gelatinization starch granules, and determines the long-term development of structure and crystallinity in starch systems. So this is known as the retrogradation process. You just think about the gelatinization. This is the opposite way of retrogradation. And we retrograde. We come back with the starch granules. Okay. That's the main thing that I have to emphasize here. So let's have a break and then meet at the second hour.